Hi everyone. So I'm gonna read the rest of the book, Feynman Lectures on Physics, and so like I said before, I don't think I'm gonna be able to, finish the entirety of it on the channel, but I'll be reading the parts of it that are just so interesting to me. And this part is kind of very interesting: conservation of energy. What is energy, right? That's like a big question, and it probably relates to everyone, and it's not just for people that are just so in love with physics, I guess. What is energy? In this chapter, we begin our more detailed study of the different aspects of physics, having finished our description of things in general. To illustrate the ideas and the kind of reasoning that might be used in theoretical physics, we shall now examine one of the most basic laws of physics, the conservation of energy. There is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Something like the bishop on a red square, and after a number of moves, details unknown, it is still on some red square. It is a law of this nature. Since it is an abstract idea, we shall illustrate the meaning of it by an analogy. Imagine a child, perhaps Dennis the Menace, who has blocks which are absolutely indestructible and cannot be divided into pieces. Each is the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, being curious, she counts the blocks very carefully and discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days until one day there are only 27 blocks. But a little investigating shows that there is one under the rug. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and upon looking outside, the other two blocks are found. Another day, careful count indicates that there are 30 blocks. This causes considerable consternation. What's consternation? Considerable consternation. Until it is realized that Bruce came to visit, bringing his blocks with him, and he left a few at Dennis's house. Bruce in, and then everything. No. After she has disposed of the extra blocks, she closes the window, does not let Bruce in, and then everything is going along all right. Until one time she counts and finds only 25 blocks. However, there is a box in the room, a toy box, and the mother goes to open the toy box, and the boy says, "No, do not open my toy box," and screams. Mother is not allowed to open the toy box. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box at a time, and when she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again, subtracts 16 ounces, and divides by 3. She discovers the following. Number of blocks seen, weight of box, subtracted minus the 16 ounces, divided by 3 ounces, constant. Yeah. There then appear to be some new deviations, but careful study indicates that the dirty water in the bathtub is changing its level. The child is throwing blocks into the water and she cannot see them because it is so dirty. But she can find out how many blocks are in the water by adding another term to her formula. Since the original height of the water was 6 ounces and each block rises the water a quarter of an inch, this new formula would be number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces plus height of water minus 6 inches divided by 1 4 inches. In the gradual increase in the complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula or a quantity which has to be computed, which always stays the same in her situation. What is the analogy of this to the conservation of energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away the first terms in 4.1 and 4.2, and we find ourselves calculating more or less abstract things. The analogy has the following points. First, when we are calculating the energy, sometimes some of it leaves the system and goes away, or sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any in or taken any out. Second, the energy has a large number of different forms, and there is a formula for each one. These are gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up the formulas for each of these contributions, it will not change except for energy going in and out. It is important to realize that in physics today, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not that way. However, there are formulas for calculating some numerical quantity. And when we add it all together, it gives 28, always the same number. It is an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. Gravitational potential energy. Conservation of energy can be understood only if we have the formula for all of its forms. I wish to discuss the formula for gravitational energy near the surface of the Earth, and I wish to derive this formula in a way which has nothing to do with history, but is simply a line of reasoning invented for this particular lecture to give you an illustration of the remarkable fact that a great deal about nature can be extracted from a few facts and close reasoning. It is an illustration of the kind of work theoretical physicists become involved in. It is patterned after a most excellent argument by Mr. Carnot on the efficiency of steam engines. Our point here is not so much the result, which in fact you may already know as the possibility of arriving at it by theoretical reasoning. Consider weightlifting machines which have the property that they lift one weight by lowering another. Let us also make a hypothesis that there is no such thing as perpetual motion with these weightlifting machines. In fact, that there is no perpetual motion at all is a general statement of the law of conservation of energy. We must be careful to define perpetual motion. First, let us do it for weightlifting machines. If when we have lifted and lowered a lot of weights and restored the machine to the original condition, we find that the net result is to have lifted a weight, then we have a perpetual motion machine because we can use that lifted weight to run something else. That is, provided the machine which lifted the weight is brought back to its exact original condition. And furthermore, that it is completely self-contained, that it has not received the energy to lift that weight from some external source, like Bruce's blocks. A very simple weightlifting machine is shown in figure 421. For what? How do you say it? This machine lifts weights for 3 units strong. We place 3 units on one balance pan and 1 unit on the other. However, in order to get it actually to work, we must lift a little weight off the lift pan. On the other hand, we could lift a 1 unit weight by lowering the 3 unit weight. Simple weightlifting machine, yeah. If we cheat a little by lifting a little weight off the other pan, of course, we realize that with any actual lifting machine, we must add a little extra to get it to run. This we disregard temporarily. Ideal machines, although they do not exist, do not require anything extra. A machine that we actually use can be, in a sense, almost reversible. That is, if it will lift the weight of 3 by 3 by lowering a weight of 1, then it will also lift nearly the weight of 1 the same amount by lowering the weight of 3. We imagine that there are 2 classes of machines, those that are not reversible, which includes all real machines, and those that are reversible, which of course are actually not attainable no matter how careful we may be in our design of bearings, levers, etc. We suppose, however, that there is such a thing, a reversible machine which lowers 1 unit of weight, a pound or any other unit, by 1 unit, but by 1 unit of distance, and at the same time lifts a 3 unit weight. Call this reversible machine. Machine A, suppose this particular reversible machine lifts the 3 unit weight at distance x. Then suppose we have another machine, machine B, which is not necessarily reversible, which also lowers a unit weight, a unit distance, but which lifts 3 units at distance y. We can now prove that y is not higher than x. That is, it is impossible to build a machine that will lift a weight any higher than it will be lifted by a reversible machine. Let us see why. Let us suppose that y were higher than x. We take a 1 unit weight and lower it 1 unit height with machine B, and that lifts the 3 unit weight up a distance y. Okay, maybe I need to look at these pictures much more, these figures. A reversible machine, okay. All right. I think I need to look at it closely. Oh. That's interesting. Okay. Reversible machine is the best. Where was I? Suppose, where was I? We would therefore have perpetual motion if y were higher than x, which we assumed was impossible. With those assumptions, we thus deduce that y is not higher than x, so that of all machines that can be designed, the reversible machine is the best. We can also see that all reversible machines must lift to exactly the same height. Suppose that B were really reversible also. The argument that Y is not higher than X is, of course, just as good as it was before, but we can also make our argument the other way around, using the machines in the opposite order and prove that X is not higher than Y. This then is a very remarkable observation because it permits us to analyze the height to which different machines are going to lift something without looking at the interior mechanism. We know at once that if somebody makes an enormously elaborate series of levers that lift 3 units a certain distance by lowering 1 unit by 1 unit distance, and we compare it with a simple lever which does the same thing and is fundamentally reversible, his machine will lift it no higher, but perhaps less high. If this machine is reversible, we also know exactly how high it will lift. To summarize, every reversible machine, no matter how it operates, which drops 1 pound 1 foot in it and lifts a 3-pound weight, always lifts it the same distance, x. This is clearly a universal law of great utility. The next question is, of course, what is x? Suppose we have a reversible machine which is going to lift this distance x, 3 for 1. We set up 3 balls in a rack which does not move, also shown in figure 4.1, 4.2. One ball is held on a stage at a distance 1 foot above the ground. Okay, 1 foot above the ground. Sounds fine. Okay. Sounds fine. As shown in, okay. One ball is held on a stage at a distance 1 foot above the ground. The machine can lift 3 balls, lowering one by a distance 1. Now we have arranged that the platform which holds 3 balls has a floor and 2 shelves. Arrange that the platform which holds 3 balls. Okay, I'm sorry. I was about to burp, but no. Which holds 3 balls, has a floor and 2 shelves, exactly spaced at distance x and further, that the rack which holds the balls is spaced at distance x. First, we roll the balls horizontally from the rack to the shelves B, and we suppose that this takes no energy because we do not change the height. The reversible machine then operates. It lowers the single ball to the floor and it lifts the rack at distance x. Now we have ingeniously arranged the rack so that these balls are again even with the platforms. Thus, we unload the balls onto the rack. Having unloaded the balls, we can restore the machine to its original condition. Now we have 3 balls on the upper 3 shelves and 1 at the bottom. But the strange thing is that, in a certain way of speaking, we had not lifted 2 of them at all because, after all, there were balls on shelves 2 and 3. Oh, wow. That sounds very stupid. Doesn't sound stupid, actually. It sounds very twisted. Yeah, it is strange. The resulting effect has been to lift 1 ball at distance 3x. Now, if 3x exceeds 1 foot, then we can lower the ball to return the machine to the initial condition. And we can run the apparatus again. Okay. I think I'm getting the gist of what's happening, but I'm not sure if it's accurate, if the perception of mine is actually what's happening. Yeah, I don't know. I have to read it again. Therefore, 3x cannot exceed 1 foot. For if 3x exceeds 1 foot, we can make perpetual motion. Likewise, we can prove that 1 foot cannot exceed 3x by making the whole machine run the opposite way, since it is a reversible machine. Therefore, 3x is neither greater nor less than a foot. And we discover then, by argument alone, the law that x is equal to 1/3 of a foot. The generalization is clear. 1 pound falls a certain distance in operating a reversible machine, then the machine can lift p pounds, this distance divided by p. Another way of putting the result is that 3 pounds times the height lifted, which in our problem was x, is equal to 1 pound times the distance lowered, which is 1 foot in this case. If we take all the weights and multiply them by the height at which they are now above the floor, let the machine operate and then multiply all the weights by all the heights now. Again, there will be no change. We have to generalize the example where we moved only one way to the case where when we lower one, we lift several different ones, but that is easy. We call the sum of the weights times the height's gravitational potential energy. The energy which an object has because of its relationship in space relative to the Earth. The formula for gravitational energy then, so long as we are not too far from the Earth, the force weakens as we go higher, is gravitational potential energy for one object equals to weight multiplied by height. It is a very beautiful line of reasoning. The only problem is that perhaps it is not true. After all, nature does not have to go along with our reasoning. For example, perhaps perpetual motion is in fact possible. Some of the assumptions may be wrong, or we may have made a mistake in reasoning. So it is always necessary to check. It turns out experimentally, in fact, to be true. The general name of energy, which has to do with location relative to something else, is called potential energy. In this particular case, of course, we call it gravitational potential energy. If it is a question of electrical forces against which we are working instead of gravitational forces, if we are lifting charges away from one other charges with a lot of levers, then the energy content is called electrical potential energy. The general principle is that the change in the energy is the force times the distance that the force is pushed, and that this is a change in energy in general. Change in energy equals force multiplied by distance force acts through. Look at this figure. Does it make sense to you? I don't know if it makes sense to me. Yeah, it does make sense to me, I guess. It's probably the gravitational potential energy that is moving the boulder up the hill. That's how I can explain my own understanding. Yeah, I know it's limited understanding. We will return to many of these other kinds of energy as we continue the course. The principle of the conservation of energy is very useful for deducing what will happen in a number of circumstances. In high school, we learned a lot of laws about pulleys and levers used in different ways. We can now see that these laws are all the same thing and that we did not have to memorize the 75 rules to figure it out. A simple example is a smooth inclined plane, which is happily a 3-4-5 triangle. We hang a 1 pound weight on the inclined plane with a pulley, and on the other side of the pulley, a weight W. We want to know how heavy W must be to balance the 1 pound on the plane. How can we figure that out? If we say it is just balanced, it is reversible, and so can move up and down, and we can consider the following situation. In the initial circumstance, which is called A, the 1 pound weight is at the bottom and weight W is at the top. Okay. When W has slipped down in a reversible way, we have a 1 pound weight at the top. And the weight W, the slant distance B, or 5 feet from the plane is which it was before, in which it was before. We lifted the 1 pound weight only 3 feet, and we lowered W pounds by 5 feet. Therefore, W is 3/3 of the fifth of a pound. How do you say that? Three. Well, I never learned mathematics in English, so it's probably very hard for me to say it in English, but we're gonna move on. Note that we deduce this from the conservation of energy and not from force components. Cleverness, however, is relative. It can be deduced in a way which is even more brilliant, discovered by Stevinus and inscribed in his tombstone. Figure 44, what's 44? The epitaph. Epitaph. What's an epitaph? It has to be third of a fifth. What? 3/5. Can you say it like that? Anybody here who's listening to me and can comment on this? Because I don't know how to say it. Because the chain does not go round. It is evident that the lower part of the chain is balanced by itself, so that the pull of the 5 weights on one side must balance the pull of 3 weights on the other, or whatever the ratio of the legs. You see, by looking at this diagram, that W must be third of a fifth. I'm doing it again. I don't know what to call it, of a pound. If you get an epitaph like that on your gravestone, you are doing fine. Let us now illustrate the energy principle with a more complicated problem. Let us, the screw jack shown in figure 4 to 5, a handle 20 inches long is used to turn the screw, which has 10 threads to the inch. We would like to know how much force would be needed at the handle to lift 1 ton or 2,000 pounds if we want to lift the ton 1 inch. Say then we must turn the handle around 10 times. When it goes around once, it goes approximately 126 inches. The handle must thus travel 1,260 inches. And if we use various pulleys, etc., we would be lifting our 1 ton with an unknown smaller weight applied to the end of the handle. So we find out that W is about 1.6 pounds. This is a result of the conservation of energy. Okay, so it's probably better for me to just like finish it right here, and I'm gonna highlight this so that I don't forget that I was here. And I don't know if I'm gonna read it out loud, the rest of it, because it really is difficult to read out loud. You have to kind of study it, not to read it, to actually understand what's happening. So I think I'm not gonna be able to read the rest of it out loud. Then I'm gonna have to study it for myself. Oh, this formula, I can remember this formula. This is actually beautiful. And then we go to motion. That's beautiful. It's just so beautiful. Yeah, thank you for listening to me.